By the way, because you and I are starting from the beginning of this calculus course, I would recommend we spend at least a couple minutes today understanding the big picture before we kind of get into some of the details, right? It's kind of like before you navigate the ocean, you want to understand what does the map say. Let's look at the larger map. One way to define algebra and algebra 2 is that they are the mechanics of math. One way to define, you might call it algebra 3 or pre-calculus or college algebra, depending upon where you took it. You would call that introduction to functions. Okay, so in other words, you're understanding this idea of input-output in terms of the shapes of functions. But in that class, like for example, unless we had like a parabola, we couldn't find its max or min from vertex. Like if you had like a cubic where it was like up and down, unless you plug into the function, you can't find where the max and min are. So another way to call calculus is essentially function analysis. And one other thing I want to put into your head, you probably already realized this, but it's definitely an important thing to note. Calculus mostly studies rate of change. Does that sound familiar?
Yes.
Okay, so it turns out until we get to calculus, we don't really understand how things change mathematically, at least on a deep level, compared to the functions themselves. If you're in, let's say, algebra, and I give you the formula for the volume of a right circular cone, so you've got some sort of right circular cone here, and say you fill it up with a certain amount of snow cone, right? Like summertime, so you fill it up with snow cone. And suppose I say, okay, this is the radius of the amount of snow that's in the snow cone, and I also know how much volume is in there. Can you calculate the height? Yeah, that's just a formula, right? 1/3 pi r squared h equals v. Divide by everything except for h, you just get h by itself. So it's an algebra / geometry problem. But then here's where calculus is different. In calculus, I might be saying, suppose syrup is being poured into the right circular cone at a certain rate. How much is the height rising depending upon how much volume is going in per unit time? Now suddenly that's a very different question, right? Because it's not what is, it's the question of what's changing. You see the difference? All right. Consider f of x is the square root of 4 minus x. Find the derivative of f at the point x equal a using the definition of the derivative. That is, find f prime a using the definition of the derivative. Okay? B, find the equation of the line tangent to the curve f of x when x equals 3. C, state the domains of f of x and f prime x. Okie doke. So let's have a think about this. So we want to use the definition of the derivative. So part A. So the question is, what is that special formula for the definition of a derivative? It's the limit as h approaches 0 of f of x plus h minus f of x over h. If I took off the limit, then f of x plus h minus f of x over h would be the slope of what line between 2 points? You were starting to say this a moment ago, starting with an S.
The secant line?
The secant line. Okay, so let's have a think about this. The secant line is the average rate of change over the interval h, whereas the derivative is the tangent line, and it's the what kind of rate of change?
Instantaneous.
The instantaneous rate of change, right. So the way I like to conceptualize this is, suppose you're looking at a cheetah running across the savannah. F is its position, and X is the time. You know, so a cheetah, I mean, one of my most favorite, can go from 0 to 60 miles per hour in 4 leaps. Incredible. Unbelievable acceleration. But here's the point. The cheetah might go from 0 to 60 miles per hour, and you might say that in the first, let's say, 4 seconds, as the cheetah is doing the leaps, the secant line slope is, let's say, 27 miles per hour. Suppose x is in miles at or sorry, F is in miles, and then X is in hours. But then you might also be interested in what's the cheetah's speed at the exact moment of, let's say, 2.7 seconds, for which you'd be calculating the derivative. Now think about this. Based on a theorem we're going to relearn later this semester, if you remember what's called the mean value theorem, do you remember this? If the cheetah goes from 0 to 60, that means the average rate of change needs to be somewhere between 0 and 60. That's why I chose the number, let's just say out loud, 27 miles per hour. But the point is, you can just conceptualize that all in your head to understand the difference of average rate of change versus instantaneous rate of change. The average rate of change is the secant line. The instantaneous rate of change is the tangent line. And by the way, the tangent line, that's why we shrink down h to 0. Because there's no longer an interval, 0 to 4 seconds, there's just one moment. Is that okay?
Yeah.
All right. So this is what we're doing for part A. Okay, next question. What do we then start filling in for f in this formula?
Our function?
That's right. So we're going to say f prime x is equal to, the limit is h approaches 0 of, and then what do I put in around the x plus h and the x instead of f?
First one would be square root of 4 minus x plus h.
Beautiful.
Minus.
Exactly. Now, by the way, I see, did you notice I used parentheses and I got a minus sign there?
Yes.
That's because the minus needs to what with the x plus h?
Distribute.
Definitely, distribute to both terms. Now, a very important thing is about to also come up. Yes, we could distribute the minus to both terms, but how in the world can we kind of get things to work themselves out when doing this definition of a derivative? In other words, we need to get terms to combine and things to simplify, right? How in the world can we do that when we have such a complicated expression with square roots? Generally, in this course, when working with, let's say, complicated square root expressions that are summed or subtracted, it is a good idea to use the conjugate to simplify an expression. Okay, so that's just my general wisdom there. Okay. Now, by the way, there's actually an important reason why we're going to do that. Whenever we have this limit as h approaches 0, now, by the way, this actually goes all the way back to Newton, because Newton was thinking, oh my gosh, if I'm dividing the denominator by 0, suddenly I'm in trouble. Because think about it, right? Whenever you divide by 0, bad things can happen. Except if they don't. Because if we're dividing by 0, in some sense, we're not dividing strictly by 0 because we're taking a limit. But furthermore, can we get things to simplify such that it's not as much of a problem?
Yes.
Yes. Okay, so let's actually write this down. This is a very important concept, okay? We expect, okay? So I use the word expect in caps because if I've been kidding thus far today, this time I mean it. So we expect that a derivative by definition will simplify, okay, so that the final expression can be calculated, okay? So that's something we always expect when doing a derivative by definition. To accomplish this, we need to have, and then what's the condition? What do we need to have happen on this derivative by definition for this to occur?
We need to have the denominator not equal 0.
You're pretty close. So the thing is, the denominator, the limit is having h approach 0 anyway. So do we really want that to stay, or do we want that h to cancel?
Oh, to cancel.
Yes. So to accomplish this, and I'm going to highlight this, we need to have the h cancel from top and bottom. Does that make sense? That is not negotiable. We must have that happen. So the reason I bring this to your attention is, given that's not negotiable, let's take a look at the derivative that we have in our case. So we have a square root, and then we have 4 minus x plus h, and then minus 4 minus x. Now, if you think about it, it's like, oh my gosh, the h is trapped, if you will, inside of a square root. So in order to simplify that expression, we want to use the conjugate. Because in some sense, once we use the conjugate, we're going to be extracting the h out of the numerator. And once we extract the h out of the numerator, will we be able to get a bunch of the terms that aren't involving h to cancel?
Yes.
Yes, we will. And then in the final analysis, will h cancel from top and bottom?
Yes.
Yes, it will. And then we can finally be at our derivative. Does that make sense?
Okay. Yeah.
Now, by the way, there's a few more details, but that's basically the notion where we're headed. Is that clear?
Yes.
All right. So I'm going to suggest we use, as we already discussed, the conjugate. So let's go next slide.
Yes.
So what would the conjugate of this look like to apply? So I think it's like that. Now, it's pretty complicated look, but you see it's just the conjugate, right? Mm-hmm. So this right here is multiply by the conjugate. Get top and bottom. Right? Because that's algebra legal, so to say. All right, so let's apply this conjugate. Now, whenever you multiply something by its conjugate, you apply the what pattern from algebra?
Like FOIL? Because you're...
Yeah, you're applying FOIL. And in particular, you're applying what special pattern of FOIL? Okay, so what if I take a minus b times a plus b? So yeah, a minus b times a plus b is the what pattern?
I mean, I can do it out, but I don't know if I ever... Oh,
The difference of squares, right?
Oh, okay.
So the thing is, you're applying the difference of squares pattern.
Okay.
So give me 1 second here. Let me switch colors. Yeah. Okay. So we're going to apply this difference of squares pattern. Okay. To this, to the numerator, right? Okay, so if that's the case, then we could just sort of apply it. So a in this equation above, a is just like that big square root with the x plus h. B is the square root with the 4 minus x. So we're essentially just going to end up squaring them. Would you agree? Now, when you square a square root, what happens? Right. In other words, they're just inverse functions. Right. So I'm going to suggest that we just literally get what's inside the radical. Okay. And then should we also get inside what's inside the radical of the second one?
Yes.
Yeah. So for both. Okay. So in the numerator, we got 4 minus, still in parentheses, x plus h. Minus, now we got to be careful here. So it's minus the entire 4 minus x on the second term. You agree? Mm-hmm. So let's write the words apply to numerator. Numerator. And careful with the parentheses. Parenthesis. Right? So you got to be algebra careful. And the denominator, I think that what do you call it? I think that the conjugate just remains, right? But then there's still the h there. So you got the h on the outside. Okay, there we go. I just made the parentheses bigger. Are we good with all that?
Yes.
All right. So next thing, can we apply the minuses throughout the numerator? because there's two minuses to be distributed. Yeah, absolutely. Now, by the way, let's go back to our concept, right? We need to have the h cancel from top and bottom. So if you think about it, here's an important thing. All terms not involving h should then what? So all terms not involving h will eliminate. Okay, maybe let's use the word eliminate, just because eliminate, typically adding and subtracting. Okay, so now we're at that lovely step. What happens to the positive 4 and the negative 4?
Cancel.
Definitely. Yeah, same thing. Yeah. I'm not too upset either way. Yeah. And then how about the plus x and the minus x?
They also cancel.
Yeah, exactly. Okay, so we could just see it there. And then so we just get negative h for the numerator, right? Okay, we are almost home. Now comes that very important moment that, in fact, just to make sure we're clear, I'm even going to use the highlighter, right? We need to have h cancel from top and bottom. So, back to here, are we now set up for success? Yeah. So can we cancel the h from top and bottom?
Yes.
Okay, so let's write this down. Now, cancel the h from the top and bottom. Okay. Now, by the way, part of the reason I'm just sort of writing it out here is it's at this moment that we really need to bring the limit back in. So up to this point, we've been a little bit loosey-goosey with like not worrying about the limit part. But once we get to this next line of algebra, yeah, we need to bring the limit back in. Okay, so we're almost there. Almost there. Okay. What's the very last step? We haven't really discussed this yet, but why did I bring the limit back in? What's the very last step?
To substitute in 0.
Yes, exactly. So, nicely done. So we're just going to apply h being 0. Okay, so it's just going to be literally just right there. Okay? Now, by the way, sometimes it's in both the numerator and denominator, even after you're working out the definition of a derivative. In this case, it's only in the denominator, but anyway. Now, by the way, do you see that if I applied h equals 0 there, wouldn't you just have 4 minus x in the first term? And then we've got another 4 minus x square root in the second term. So how many of those will there be?
2.
So I think there's going to be 2 of them. So I think in the final calculation, we can just write negative 1 over what? Nicely done. 2 square root of 4 minus x. And that would be our derivative by definition. You see how that works?
Yeah.
Now, by the way, one last thing. If you're asked to do this on an exam or it really counts, I recommend, especially given that you've run through some of this course before, that did anyone ever make it a crime to rewrite the original function and use the shortcut method, or let's say the chain rule or whatever, for derivatives, and then make sure that we got the right answer?
Nope.
No one ever made it a crime. So I'm going to suggest we just do that, and it should only take but a moment. Do we want to stick with square roots, or do we want to go for what kind of powers on functions?
1/2.
Yeah, just the 1/2.
Because the square root, yeah.
Yeah, so in other words, we're going to go for fractional exponents. So if that's the case, then now I think we're set up for success to take the derivative, right? So let's take the derivative using the chain rule. So the way I like to say it is the chain rule is the derivative of the outside, keep the inside function, and then times the derivative of the inside function. So it's like that. 1/2 drops down, 4 minus x to the negative 1/2 power, and then times the derivative of the inside. The derivative of the inside is negative 1, because that's the derivative of 4 minus x with respect to x. Now, are we going to end up with the same thing that we calculated before?
I think so.
Yeah, because it's going to be a negative 1, the 2 is downstairs, and the square root. So remember,
Right.
if you have a negative, that drops it to the bottom. So like that. Then, let's see, can I multiply negative 1 to the numerator?
Mhm.
Yeah, nobody gets their feelings hurt. And then last but not least, I mean, is 1/2 times this just going to give us exactly what we had here? Yeah, it's just 1/2 times it, and because we could just write that as a square root. Okay, so we know we got the right answer, so that's comforting. Any questions on part A? By the way, you and I went through a lot of more steps and explanations so that you're ready for other things. But I think part A is probably the longest or hardest part of this problem. I realize part A is not 100% done. Okay, so let's go back for a second here. So this is an aside, the checking the answer. So let me just write this down real quick. Okay, so we didn't have to do that. Now, at this point, let's not even put a box around this necessarily yet, because this is the derivative for any function, or sorry, the derivative for any x value, I should say. Okay, it's better said. Okay, but specifically, they want us to plug in what for x?
Oh, okay. X equals A.
X equals A. Okay, so that's why I said we should proceed one other further little step. Now we're just going to have x equal what?
A.
X equals A. Okay, so that's what the derivative looks like if we plug in A. Now for part B, we're going to say let x equal A, but what's the value of A that we're actually plugging in?
Oh,
3.
okay.
Do you see that? We're just going to allow it when it's 3. So A, which is the value that we allow, is 3. By the way, keep in mind, they're walking you through the problem, right? It's the derivative with a certain value plugged in, and that value is 3. Okay, so I think all we got to do is we're just going to say let x equal 3 here. 3 and 3. Like so. Then, let's see, and then it's just order of operations, right?
Yep.
So what do we do first?
So in the square root, it's
Yeah.
just
1, right? And the square root of 1 is just 1.
1.
Okay.
So then it should just be negative 1/2.
I think so. Right, because the square root of 1 is 1. And just so it looks a little nicer, let me put the negative out front. All right.
There we go.
There we go. All right, we good with that? That was it for B.
Yeah.
That was easy. All right, and then finally part C. So let's go back to see what they asked about for part C. Yeah, state the domains of f of x and f prime x. Okay, so let's talk about domain. So domain is kind of a pre-calculus idea, right? Remember we were talking about inputs and outputs? So does domain pertain to x or to y? Yeah, to x. And then here's the deal. Do square roots have domain restrictions? Right, so we can only take the square root of what kind of number? Or 0. Yep. So you might say a non-negative number. Yep. So we can take the square root of a positive number or of 0. So that means the radicand, which is the quantity under the radical, right, must be, what inequality can we use to mention those things?
Greater than or equal to 0.
That's the one. Nicely done. Okay, so let's go down here to part C. And let's say domain of the function f of x is such that we've got 4 minus x. Oops, sorry, 4 minus x greater than or equal to 0. Okay, so far so good. Then how do we get on to solving that inequality?
We can add the x to the other side.
I agree. We can just add x to both sides. So that's just going to be 4 greater than or equal to x. Okay. And while that is technically correct, hopefully you're aware, typically we like to read things from left to right, where x compares to 4. So how could I rewrite this so that x was on the left-hand side?
X is less than or equal to 4.
Correct, right. Because if 4 is greater than or equal to x, that's just exactly the same thing as saying x itself is less than or equal to 4. Okay, in other words, it's smaller or the same as 4. Are we good with that?
Okay, yeah.
Now, one last thing. do we usually leave it in inequality form, or do we do interval notation?
Interval notation.
Yeah, so let's go interval notation. Okay, so this is just kind of how we go in calculus. So what would this inequality be expressed in interval notation?
Parentheses, -4, bracket
Yes.
with a U, and then, or union, bracket for infinity, parentheses.
So you were exactly right on the first interval.
Okay.
Because if you were doing everything but the number 4, then you'd be correct.
Oh, yeah, okay.
But if you're including 4 and nothing else, then it'd just be this interval.
Okay, because it has
Okay.
to be less than, it's not. Okay, yeah.
Yeah, just less than 4 and including 4, and that's it.
Right.
Okay? All right, so I think that's the answer for C for the function. Okay? Can we do something very similarly for the derivative?
Yes.
Yeah, for the derivative, yeah. Does the fact that the denominator has a square root in it also still apply in terms of the stuff we have here? In other words, must the radicand be greater than or equal to 0? 4 minus x greater than or equal to 0 is definitely true for the derivative as it relates to the square root part, right? Okay, so for the square root part. However, do we have an additional piece, in other words, possible domain restriction, because we've created a fraction?
Yes.
Yeah, and in fact, we can't let the denominator equal what value?
0.
Correct. So we also don't want the denominator to equal 0. So what should also be excluded?
What should also be excluded? 0?
Yeah, the 0 itself.
Yeah.
In other words, what we're really going to have is we're really going to have 4 minus x is just greater than 0. Right? Because we don't want it to even equal 0. Okay? So don't have the radicand equal to 0 either, is basically the idea, right? Okay. Now, do you think that it's going to work itself out very, very similar?
Yeah.
It's going to work itself out very, very similar, except we're not going to have the equal to part, right?
Mm-hmm.
And then in the interval notation, will we have a bracket on the 4 or instead a what?
A parentheses.
A parenthesis. And I think that'd be our answer.
Great.
Do you see how that works?
Yeah.
All right.